of rivets before we get into some kind of a theory or some numericals. To begin with, rivets were the very beginning or very first form of joints, or to be very simple, permanent joints which were used in any metal industry. So it started with the basic applications of in boilers and ships. So early days ships which were transited from an wooden-based ship and which went on to steamer ships used riveting operations to make the whole vessel. Second thing, the boilers which we have been using for quite a large number of time, it has got thick plates which is riveted from end to end to make a whole composite unit. Then we have got two forms of riveting. One is called hot riveting, where we will be heating the plate and the rivet in up to a temperature of 1100 degrees centigrade, which is almost the recrystallization temperature. The material which we generally use is plain carbon steel, sometimes medium carbon steel. The time where those steels were the most advanced steels available. You heat it, then we use press-fed mechanisms. You use a hammer and then blow it and pierce it into that particular place. Second form is called cold riveting, which is mostly used in non-ferrous material. So when we call non-ferrous material, it is anything from aluminium, zinc, magnesium, anything which is not ferrous-based systems. So the failure in hot riveting mechanisms or hot riveting operations is mainly due to tensile, because you have got rivets which gets teared or which get broken because of movement along that plates. In case of a non-ferrous or cold riveting operations, we have got shear failures because there are two plates which tend to elongate over a period of time. So we'll start with an example of some applications which you have already seen, which you might be aware of. These photographs gives you a little bit of knowledge or memory of how these things would have been made. Asia's largest, Asia's biggest, longest, and number of things which comes into the first picture called Howrah Bridge. It's in Calcutta. It was built almost 100 years back. Whole structure is a suspension bridge, and at the same time it is fully metal riveted system. So which means you can just imagine when the people were building this structure, we had to rivet it at the top, in the middle, or in the bottom of that particular bridge. So you have to heat it and put those rivets in a specific location. Second thing, most iconic, or we could generally say it is most extreme railway which you can find all over the world. Paman Bridge in Rameshwaram. It's one of its kind of a cantilever bridge or foldable or replaceable kind of a bridge. Again, it's a steel structure built with a large amount of riveting operation. The third, I'm not sure, it's quite, it comes in a list of Asia's longest bridges. It is across a river called Godavari in Andhra on a place called Rajamandri. The length of this bridge or the width of the river at that particular point is 3.5 kilometers. So you can just imagine how long the bridge has been made using your riveted operations. So all those things in all these systems, the very common point which we notice is you have to make this riveting operation in situ, which means you have to do it in that particular place. Unlike today's condition where you can build it somewhere else and just join them. So major part of them is you just have to first make a hole on the plates, then you have to use those rivets again, which is hot enough, and then you have to pierce it in that particular hole. So it's simply joining two metals, two plates together and matching the hole, which will be held together by means of rivets. So the next point, this is the present day technology where it is form of a cold riveting used in non-ferrous material. The machine or a gun which we generally see, it works with the help of a pneumatic hose. The pins which you can see over here has got a head, a rivet head, which is fixed onto this plate on a component below. So this is kind of a riveting gun. It's called riveting gun, where you are going to pierce rivet using pneumatic force. You don't have to hit it with a hammer, and when you pierce it, and it can be done in a continuous fashion. So on the left side, you can see rivets ready on a thin strip of a plastic. On the right side, you can find the rivets has been already pierced into the hole, into the plate, which will finish your job. So in this riveting operation, you employ less amount of force, and we can do it for a non-ferrous material. In this case, it's an aluminium sheet added with aluminium rivet. We use it when we are utilizing some construction-based industries. So going to the next point, since we are more aware of welding, I'll just give you a comparison between the welding operations and the riveting operations. So what we see as an advantage, riveting can be done for both ferrous, non-ferrous. In case of a welding, we have got few welding options for a non-ferrous material. It's very tough to fuse aluminium, magnesium or zinc, any non-ferrous material, as easy as you can do it for a ferrous material. Riveting can be done for both ferrous and a non-ferrous material. Second point, riveting is generally used in your areas where you have got more vibrations or more kind of an impact. Boilers, it's most commonly used. And then you use it in bridges where you have got more impact or more vibrations. Ships, which generally undergo very long voyages. The third, it's an easy to inspect when you do a riveting operation. So you just have to check if both the plates are joined together, and we then go ahead with some amount of inspection on checking if rivet has clearly pierced through that particular system. And fourth point, it causes less damages even after you try to dismantle it. So we just have to use a tool to remove the rivets, and when you see that place where the rivet was available, it will have a very minimal damage on that. When you just find a comparison between this and a welding operation, the first point, as I said, you can do in a large context for a ferrous material, but non-ferrous, you have got a limited options. Second, you cannot use it in vibrations or impact-based system because the zone where you have done already a welding has already undergone enough amount of heat and thermal distortions. You hit it exactly on the welding joint or a weldment or heat affected zone, there are high chances that the material will break. The third point, inspection of a welding joint is quite phenomenally big work. You have to do a large amount of destructive or a non-destructive test. When you inspect a welding joint, you will be utilizing something known as dye penetrant or radiography or any other thing. And when you try to dismantle a weld joint, you will be totally damaging the joint and the workpiece. It's very tough that you can recover back the parent material after you remove the welding joint position. The limitations, the reason why we moved out from riveting to welding after, even if we have got these many plus points, is we got a high labor and material cost. Earlier days when we had a discovery of steel and coal, there was large amount of people who were available. The Howrah Bridge, which I showed to you, involved almost 1 million of people working at the same time or in a particular cycles. So we cannot do it now. There are many issues with the cost of the labor and the material. Second, there is more noise during fabrication. You would know that when you hit a nail on a wall or on a particular material, the amount of noise which you hear is almost 100 times more when you are doing riveting operations simultaneously on the whole system. So you can just imagine 1,000 rivets being pierced into the plate simultaneously, that too hot with more amount of chaos. So due to the safety standards and other regulations, people are getting it down to your non-riveting operations. And the last point, as per design, there is more stress concentration on that point. Reason, when you want to make a rivet, you just have to make a hole, a punching operation or piercing operation. And after you add a rivet in that, there are chances of more stress concentration in that particular area. So, we will look on to the design factor. Some options of the kind of rivets which we will be utilizing in this particular portion. The most common is the first two, a snap head and a pan head system, where you just have to use a riveting gun to pierce it through your system. The other things which you see in the countersunk or round sunk systems, they are mainly used when you have very critical operations, whereby you are combining two plates with a lesser amount of distance. Second thing, we use them when you don't want any systems, like these heads will be outside the plates, outside the sheet metal. But when you use a countersunk, when you use any of these flathead or countersunk, they'll be almost on the same level of the sheet metal or a plate, which means it won't cause any obstructions if you're using any added material into them. So even if you do a riveting, you close it, you won't even see riveting operation has been done. So to give an example of these things, the last three, you would have seen in buses, there is a small steel plate which is added on the side surface of the bus. It is generally used to avoid any damages if a bus is collided on a sideways. So how to join those systems? You need to use a small nut or a rivets, which we generally use a flat countersunk or a round countersunk. Add it on that system, which is using a riveting gun, and finally you'll be able to close that system. So there are few types on this which we have seen. We'll just go through the joints. The joints which you see over here is almost the same which we have been seeing in your wooden structures, even steel structures, which is called lap joint. Adding two plates one above another, you have got multiple systems. We will going for the other joint. So we add a rivet, this double-headed or both side closed rivets. The second which you see is called a butt joint, where the actual metal, the actual piece of thing which we need to join is these two. So to join these two plates, we are adding an additional plate above that so that it can grasp or it can hold the plates, and finally you add a rivet on that. So butt joint, as we do it in your wood or a steel in case of a welding, is similar, but in case of a rivet, we add two more extra plates at the top and at the bottom just for the sake of holding your rivets. You cannot join two metals or two sheets using a rivet, like half rivet on one plate and a half on the other. It will cause stress concentration, you cannot hold it. So to avoid that, we add two plates on the top and the bottom surfaces. So the next point, we'll see an arrangement which will give you an idea. There are few key terms which you have to know before we get into how riveting operation is generally done. Pitch, as we are aware, pitch is next point on the consecutive systems, and the distance between two consecutive rivets is actually called pitch. And we have got n number of rivets or rivet heads added on your plate, so we are only going to use that. Transverse pitch is a perpendicular distance between two rivets. So generally, when we use rivets, we generally get across there's a plate, and we are going to join it. So pitch is the distance between two rivets at a particular distance. Transverse pitch is something, a distance between these particular distances. So we have got n number of pitches which are added on both horizontally on an x-axis and also on a z-axis. The third point, it's called diagonal pitch. It's used in your zigzag. I'll show you that image. It's a smallest distance from two extreme rivets. We generally use it for a zigzag rivet, which means it doesn't go in a particular fashion. The fourth or margin or marginal pitch is the distance between the rivet hole on the edge of the plate. So what you see over there is this particular distance. This particular distance is called margin. And obviously we have to leave some margin when you are doing any riveting operations. You cannot go and do rivet on the edge of a system. Many reasons. There is a stress concentration, and it can shear off based on your lap joint or your butt joint. And obviously we don't have to rivet the whole plate. We have to rivet on a limited space. So going to the next terms which we are generally using it. The kinds of joint, I'll go and show you the next kinds of joint. The one which you see on the left is a kind of a lap or a chain joint. The one which you see on the right is a butt joint. So when I say lap joint, you add two plates one above another, match holes of those two plates, then finally do your riveting operation. When we do a butt joint, the main plate is intact between two different plates, top and bottom, and then we are clubbing all the three plates together. avoiding the joint where two plates are joined together. So you'll know better with reference to a diagram. This is the first lap joint. You have got many rivets being added one above another. This is just to give you an idea that these two holes need to be concentric, because the rivet has to go directly match that concentricity, and we can have any number of rivets based on your need. So this is your top plate. It is with some eccentricity or some difference with the other plate in the bottom. What you see, the distance P is pitch between two rivets. Since being a single lap joint, you don't have a transverse system in this. And then finally you have got some thickness, and we measure the dimensions with reference to the diameter of the rivet. This diameter of the rivet is known as a shank diameter, as we name it in gold, as we name it in any threaded portions. The one which you see at the top is called known as head diameter, or rivet head diameter. And we measure that distance, giving this margin and also some amount of taper, which is given so that you can avoid any kind of stress concentration on it. So the next point, we have got transverse pitch, which is mentioned with reference to R, which is going from the center diameter. Since we have got two rows, we have this distance known as transverse pitch. This is your normal pitch or a longitudinal pitch, which is difference on a particular axis. The difference on how do you understand transverse and longitudinal pitch is based on the force being applied. In this case, force is applied along these two axes, which causes the the rivet to fail under tensile load. In case if you are designing for a shear loading, your line or your design will change accordingly. Go to the next point. We have got the third, which is known as lap joint, and it is known as zigzag lap joint. And now also it's a zigzag double lap joint. So we have got bolts, or we have got rivets which are added on a zigzag fashion. So it's not in a straight line. It is you find out your transverse pitch, you find your normal pitch, and you need to find distance between two consecutive rivet holes on a zigzag direction. Now all those things are done. This is a very small scale. When you do it for a bigger scale like a boiler or bridges or any steel structures, we have to mark it. You need to precisely mark the hole, and then you have to place those rivets. The reason why we had zigzag lap joint is because we have a limited space, and when we design rivets, we find out that we need to add more rivets on a smaller area, and you don't have any space, so we go for some amount of zigzag. Second point, if you just find this PR, if you try to align this rivet hole very close to it, you don't have enough margin between two consecutive rivets in a transverse direction, which in turn gives you very lesser metal space. And when there is a stress concentration and when there is a damage on that, this will tend to break quite easily. Now, this technology or this system was evident after few shipwrecks. Most common or most infamous, I would say, is a shipwreck of Titanic, where there are many reasons why ships fail, specifically Titanic failed. One is because of a ductile brittle transition. The metal changed from a ductile material to brittle. Second thing, they have used much heavier, much bigger rivets, and they tried to fix it on a smaller space, which in turn caused huge amount of stress concentration, and it broke it. Many areas it broke exactly on the rivet joints. So we go for some difference or some kind of a zigzag system to avoid those kind of methods. We have got the same lap joint with two joints which are added together, but there is a small difference. We call this as a butt joint. We have got a single plate added on the top, and there are two different plates if you can look at it carefully. These two plates are something which needs to be joined with the help of a butt, but you cannot join them because you cannot put a rivet in this position. So there are two rivets. One will be holding this particular plate, the other will be holding the next plate, and the top plate is going to hold both the rivets, which in turn means that you can hold them together. It is almost like we have glued them together with the help of two rivets. This is for one cross section. When you go for next and many more, you can add them on a specific manner. We do this riveting joints or this kind of butt joint for material which is used in boilers. In some cases, it is done in your steel structures used in your bridges. So the next level of the butt joint, we have two plates which are added one above another, and again you can see the difference in the hatch or the cross section given here. There are two different plates, and there are two different plates which are going to hold the actual plates, and finally you are going to rivet it. Now the whole length, which is generally not mentioned here, is to give you an idea of it can go for any infinite distance. So that zigzag line gives you an idea that it is for a very longer distance. The last, before we start with some design consideration, we have got multiple plates and multiple butt joints. The first, we have got a butt joint at this point, and we use a large amount of rivets on one side itself. This purely depends on the width or the length of the system, which goes across based on your transverse pitch and also in your longitudinal pitch. Okay. So, just begin with some design consideration. This is quite unique. It's called diamond joint. It's done specifically for a butt joint. Instead of doing for a large distance of riveting, we reduce number of rivets which can be used in your whole system. So you can avoid this upper triangle. There are four triangle space which we are trying to avoid it. We reduce number of rivets and we reduce the time which is required to do this kind of an operation. This is mainly focused when you are joining two plates or two different channels in your bridges. You have got a space constraint and you cannot do a riveting operation on two particular joints. So to give you an example, we have got a steel structures which are generally built in a form of a trusses, and you have got structures like this. So when I want to join these joints and also these things, we need to be quite economical, we need to save time, and we need to be precise in joining that, because your truss structure mainly depends on the stability of those joints. So when we are adding it, you have got one joint which is fixed onto this member, and there's another joint which is fixed to this particular member. When you join these two things, we will save space, and it is mostly done with reference to your diamond joint, which is a type of a butt joint. Okay. So moving beyond, we'll just see the main theme of the design, which is focused on how the rivets fail. So basically we know the failure conditions. The rivets generally fail under tensile and shear. It is almost the same in which your bolts tend to fail. And the other kinds of failure, in case of plate, it can fail due to the crushing, it can fail due to shear in a margin area, and it can also fail due to tearing in a margin. There's a huge difference between shear and tear. First case, we'll just see, it fails under tensile. Second case, it fails under shear. The third, you can see that it fails due to the crushing. So this is the third, this failure due to the crushing of plate. Fourth, it's a shear. Plate itself shear, rivet remains the same. And fifth point, there is a crack or a tearing on your plate. Now getting back to this, you apply a force which is equal and opposite, which causes tensile failure on rivets. So the tensile failure generally occurs when you are using a material which will fail at a particular point when force is equal and opposite. Second case, it's a shear failure where the plates starts failing before your rivet fails. Crushing, your material on the plate crushes. It can be either of those plates, at the top or the bottom plates. And shear is the amount of material which is removed from the plate because of the force being applied, equal and opposite. Tearing is mainly happens because of a crack in your plate, which will tear open the top plate. Mostly it is the top plate which starts. It follows the same rules or laws of fracture mechanics. First it starts with a crack, then it propagates, then finally it breaks or tears that particular system. The last diagram is simply your idea to give an view that force when it is applied on a different plane. So more or less we have got failures of both rivets and the plate. We don't have this system in any other permanent joints. If you consider welding or even if you consider temporary joints like bolt, the most common thing which will fail is actually the fasteners. In case of bolt joint, the bolts fail before your plate can fail. Same way, in your welding joint, the welding joints fail rather than your base material. Some cases, the heat affected zone causes a failure in your joint. In case of a rivet, it can happen on both your rivets and on your plates. This is one main reason why people started avoiding using rivets in some critical operations. For a very long time, riveting was used in boilers. There were few failures exactly on the rivet joints which caused your boilers to explode. So nowadays people have moved over from a rivet joint to a welding joint. So we use submerged arc welding instead of a riveted joint. So you don't even see the seam where the welding operation has been done. In case of the previous systems, you would see number of rivets done on a boiler. To give an example, the old locomotives which were used in trains, you got a big locomotives which had a steam boiler and steam generator. Then finally you have got piston cylinder mechanism which will move your track wheel. So you could see the layer on that particular boiler which is in a riveted form. Always you would find that there are some leakages from those systems. So same way, ships nowadays they are joined with the help of a welding operations. Fine. You can just make a note of these formulae which we will take further to solve some numericals. I just mentioned that pitches, generally the rivets fail based on its dimensions. It fails based on your systems. We generally go for failures of a rivet irrespective of whichever joint it is. So it fails either under tensile or it fails under a shear. So starting with the shear failure, the last part will go for a crushing failure check also. In the next way of analysis, we'll just see how the plates can fail because of the force being applied. The first case, the shear failure is purely because of the force applied, which is mentioned as PS, and amount of shear stress which is applied on that particular material. The second case, you have got a unique system which is called as a double shear, which is again you apply it with two different, it is the double amount of force which we generally use it to check the amount of failure which can cause. So in the first case you need some force. In case of your double shear, you need double the force to break that particular system. So when will you have a double shear mechanism? When the force is applied on the rivet joint is to separate two plates equal and opposite, and it will cause the rivets to fail in two distinct locations. When you see those rivets failing, when there is a plate, there's another plate, it's considered to be a lap joint, and we add a rivet, and so when we apply a force on equal and opposite direction, there is failure on the rivet due to the shear operations. When we apply a force, just in case I have got a third plate and the rivet goes much below, there are chances that rivet fails at this cross section and also it fails at this particular cross section. So we have got a double shear or the failure of a rivet in two distinct positions. We don't have anything beyond the double shear. So in the rivet joints which have got three plates like this, we will have a chances of a double shear. In some cases, certain rare cases, even with two plates, the rivets can fail at this particular location, and also due to stress concentration, it can fail close to your rivet head position. So we calculate the single shear or double shear based on the arrangement of plates based on the rivets being used. Most common, we use only the single shear operations. The second one, it's called tensile failure, or the failure because of failure on the rivet because of tensile force acting on your rivets. So it fails because of number of reasons. One of the main reason over here is the pitch and the diameter of your material. So pitch is consecutive distance between two consecutive rivets, and it is subtracted with the D diameter, which is known as shank diameter of a rivet. Then we multiply it with T, the thickness of a plate, and the tensile strength of a material. So why we have this system of P minus D? Your tensile failure is mainly, if you just see this particular view, you have got the rivets which are being added on 2 or 3 different distinct positions. This particular distance, I can add it from center to center, is pitch. Diameter is this particular thing, and thickness, I can mention thickness of this material. Okay. So what causes any material to fail under tensile loading? It's a force and which is acting on a particular cross-sectional area. Now how do you find an area in this point? We have got 2 dimensions, P minus D multiplied by D. So T gives you a dimension in a different plane, thickness of this particular material and a surface area. So we check for a failure on P minus your diameter, which gives you a small area, and check for a failure of a rivet in that particular area. The last point, the crushing failure, which generally occurs on your rivets, and sometimes it can even occur in your plates, which is mentioned with your crushing load. Now, how to check the efficiency of the weld joint? We'll have all the 3 failures. We may have 1 or 2 failures, but in some rare cases, we have got only 1 failure. That's not quite possible, but we check for all the 3 failures in a continuous manner. So we check the efficiency with reference to 3 forces. The lowest among them is considered to check the efficiency point. So PS, PT or PC are actually failures of the strength of a rivet under shear, tensile and crushing. So if you have got the same force, same strength, which is equal to your force applied, you have got 100% efficiency. But that is rare to happen. So you have got a shear strength which is less than the force applied, tensile or crushing which is less than the force which is being applied in your system. So we check in efficiency. The recommended efficiency is somewhere between 80 to 90%. We cannot, it's very tough to go beyond 90 or 95%. So anything between them is most taken care. When you go for checking welding efficiency, it is way beyond 90 or 95%. So we try to match with your riveting operations. Okay. So I'll just go with a small numerical which will give you an idea. The contents on the left is visible to you. I'll read out. You can make a note. We'll try to solve it for a numerical. So to start with, we can use some information from your design data book also. Once we solve some numerical, I'll get to give you an idea how to check for a rivet. So what we see over here is 2 plates. These are those 2 plates, plate 1 and plate 2. They are joined with a reference to a butt joint. So you have got 2 plates which are added, the top and the bottom, and we have got number of rivets being added on a particular system. Now what kind of joint or what kind of an arrangement is this? We have got a butt joint, but we cannot call it as a single butt or double butt. It's a kind of a zigzag. You can even still mention it to be a kind of a diamond joint. So more or less it looks like a diamond. Otherwise it's a form of kind of a zigzag joint. So what are the information which is given to you? We know the pitch between 2 rivets, and we have got transverse pitch which is mentioned on it, other transverse direction. force P is applied on either side, and the job of this joint is to make sure these two plates, they don't go apart because of force P applied. So we have to design rivets according to the force being applied. Over here you have been given plate width, which is in a longitudinal direction, which is 200 mm. You're not been given thickness part of it. You are not given the dimensions of a rivet. So as a designer, we have to check if this particular joint, this is the only joint which we can make, this joint can withstand a force of 250 kilonewtons. So the maximum rivet which we can use for this arrangement is 5 plus 5, 10. It's not mandatory that we follow only this particular arrangement. If you are reducing the number of rivets, we have to increase the diameter of the rivet so that it can take care of the forces which are acting on each and every rivet. So for this arrangement, we need to check or find thickness of a plate, we need to find the diameter, shank diameter of the rivet, and finally we need to check for the forces acting on it. It's P, PT and M. P is the force, shear force, second is your tensile force, and the margin. Why it has been mentioned margin is because if that rivet is too closer to the edge of a plate, based on the riveting or the force being applied, there are chances it might cut, or the plate can undergo a failure under either either shearing or under tearing operation. So we start with finding out if the bolt is permissible, the rivet is good enough to withstand these three forces. So in case of your tension, compression, and in case of your shear, we need to check if the rivets can sustain. So under tension, it is 70 Newton per mm square. We have to check if it is withstanding that force. In second case, under compression, it is 100 Newton per mm square. Neglect that 70. And in shear, it is again 60 Newton per mm square. Don't consider that 70. Okay. So these three forces which we have to check if the rivets can sustain it, the joint is perfect. Now again, giving you an idea that why we are using only this kind of an arrangement. It's not mandatory. You can realign them and find if you can reduce number of rivets in this, what could be the change. The obvious change will be you will be increasing the diameter of the rivet. In some cases, you may even increase thickness of the plate. There are two variables which changes if you change this particular arrangement. Other things will more or less remain same. So you can just have a note, make a note of this diagram. We'll go on to solve the numerical based on this. Okay. So based on this arrangement, our understanding is every rivet will undergo failure typically under shear because you are pulling two plates two different directions. Second, the failure which might occur is tensile because these two plates might get uprooted. Crushing, we have to check under compression part of it. Also, we have to check if the plates can sustain the force being applied on it. Okay? So we only check for the plates which is in the middle. We don't check it for the plates which are at the top and the bottom position.